I'm just going to get started. Thank you all for coming today. Cross your fingers on all of the technology working. Let's put this to full screen. My name is Jean Marie Linhart. I'm going to talk to you about a journey through air under gravity, unveiling the dynamics of the flight of a sponge dart, or as I titled it originally before I put that into ChatGPT,
Uh,
ballistics
I'm
modeling
not
with
sure
a
whether it's
sponge
me.
dart.
I cannot hear anything, but it could be
Uh,
me.
um, I am not sure what's going on with somebody's sound there. Can other people hear me?
Yeah, I can hear you.
I also can hear you.
Okay, I'm gonna assume that that's going okay. This project was originally written by Peter Howard, who is a new department chair at Texas A&M University. And he originally worked on this with his wife before they had children. Um, he and his wife got together with a Nerf gun, some equipment to duct tape it to a protractor to get an angle measurement. They fired it both up in the air. They dropped some darts. They fired their Nerf gun at a variety of angles, and they took some data. So you see they've got some data here for when the initial height was with the dart was dropped from about 4 meters and fired upward from 0.39 meters. Then they have data with respect to angle. So at an angle of 5 degrees, they got a distance measurement, 10 degrees, so on, all the way up to 85 degrees. Each of these data measurements represents 4 actual measurements that were then, of course, averaged together to get the eventual final measurement. All code both in MATLAB and Python and calculations for this modeling scenario are included with the teacher version for the modeling scenario. So if you want those are certainly available. The first model that we ask the students to look at is the simple Newton's law of motion with no air resistance. So without air resistance, the only acceleration is due to gravity, which of course is in and I've got my X and my Y reversed in my graph. That's what I get for doing that at the last minute. Well, gotta laugh at myself there. So Y is upward, X is to the right there. The only acceleration is due to gravity. Without air resistance, there is no force in the X direction. We fire the dart as an angle. Of course, the angle theta is going to determine how the initial velocity is distributed. V naught sine theta in the Y direction, V naught cosine theta in the X direction. And we're often firing the dart from initial height H, which of course can, for all the times where we fire the dart at an angle, it is consistent, but when we drop it or fire it straight up in the air, of course, that can vary. You might imagine the first time I taught this project in class, I was teaching seniors taking a mathematical modeling class, and we'd of course had differential equations. And what I didn't really quite understand was that at Central Washington University, not a lot of students take physics. And so I asked students to solve these equations, and I got a whole bunch of confused looks looking back at me because they're just like, we don't remember how to do this from differential equations, and we're not sure what to do. I'm like, guys, this is a constant and that's 0. So let's just try integrating once and then try integrating again. Then I think we were all kind of back on the same page again, which helped out. When Peter taught this unit, he taught it at Texas A&M, which is a big engineering school. And so most of the students would have taken physics, and integrated into the calculus sequence there was, of course, using MATLAB. My students at Central Washington, that certainly is not true. We don't have a lot of physics experience, and often we also don't have a lot of coding experience. So it can take a while for me to get students up to speed with this. I think Peter took a while with it as well. So to do our parameter estimation in the absence of air resistance, we use the time for the dart to hit the ground after it's fired straight up. And of course, our equation for Y of t. We use the fact that Y of 2.13 seconds is equal to 0, and that finds us an initial velocity of about 10.26 meters per second. From there, we would like to figure out the distance that the dart travels. So we let TF or T final be the final time for when the dart hits the ground. And then we can calculate T final by solving our Y of T equal to 0 equation. That's a quadratic equation. So of course we get a square root in the answer. We can then substitute that into X of T to find D of theta, the distance that the dart travels as a function of the firing angle theta. This lets us get a nice plot with our data and our model on it. And then we'd also like to know at what theta we're going to actually maximize D of theta. Maximizing D of theta, so we know that this is not going to happen at an endpoint. We can look at our data, we can see that. So one of the tactics to maximize is, of course, to differentiate. Differentiating D of theta, by the way, is not very easy for the students. That might be a good time to incorporate the use of a symbolic, like Mathematica or MATLAB. Even with Python, I believe you can use symbolic Python to do some differentiating for you. I tend to coach students on how to, very carefully bookkeep and keep track of their terms here. We get this expression for D prime of theta. We want to set that equal to 0 and solve for theta. You'll notice that there are thetas all over the place. There's a sine theta there, a sine theta and a cosine theta and another term. You're not going to solve this one by hand very easily. So at this point, it's time to introduce students to using a routine. In Python, it's the fsolve routine. That's a numerical root finder. And with that use of that numerical root finder, you can find that theta is equal to 44.53 degrees is going to maximize the distance traveled. That's not exactly 45 degrees because our dart is not shot from the ground. It's shot from a height that's slightly above the ground. And so that moves up a little bit. And this is, of course, our data. So the data is in black, our curve in red. There is the no air resistance model. We can see here that we've got the general trend and shape of the data, but the model doesn't really correspond well to the data right there. They really are off. Getting my students some basics of Python and getting this far in the project at the startup of a term for me often will take me up to about 3 weeks here. I think Peter gets this done quite a bit faster than I do at Texas A&M. And again, with engineering schools, and especially if you've got some integrated MATLAB or Python in your earlier classes, that would also help quite a bit. The next model we're going to look at is linear air resistance. So in this case, our acceleration in the y direction is due to gravity, and then we have a retarding term. So our air resistance acts opposite to the velocity component in y. That's why we've got that negative sign there. And then likewise, our acceleration in the x direction, we've got the velocity, and then in the opposite of direction of the velocity, we have the air resistance term pulling the dart back and slowing it down. To solve this equation, and we could do this using second order methods. I usually use first order methods. And for students, this really looks weird. This looks like something kind of hard, not sure we can do. We could do it by maybe constant coefficients with the second order method, which of course we don't remember anymore, but this is really a first order differential equation. We just have to make the substitution that the derivative of y is equal to w. So then this is w prime is equal to minus g minus b times w, or if we rearrange that, we get w prime of t plus b of wt equals minus g. That's a linear differential equation. We can use our usual integrating factor to solve it. Once we've solved it, we've got an equation for y prime of t, which of course we can integrate to find y of t. When we get done with all the work there, we get an expression for y of t, a little bit more complicated than that quadratic equation we had in the earlier no air resistance model. Likewise, for x of t, we can solve for x prime by separating variables. And once we've got x prime, we then integrate one more time to get our x of t. Now our parameter estimation, we need both using a dropped dart. So we drop a dart from 4.06 meters. We know the time it takes to hit the ground. That lets us estimate our parameter of air resistance. And then we use the data from the dart fired straight up and this air resistance parameter to then estimate the initial velocity. And we note that this initial velocity for the dart is higher than it was in the no air resistance model. With air resistance pulling the, slowing the dart down, we needed a higher initial velocity in order to match the same data that we had before. If we look at a numerical root finder to solve for our trajectory, we can get a trajectory for theta is equal to 35 degrees. In red, that dashed line is with no air resistance. We go out a little further. With linear air resistance, we both go a little bit higher. Remember, the dart was fired at a higher velocity when we have air resistance, but it doesn't go out as far at that point. And of course, another thing we ask the students to do is to find the theta at which d of theta is maximized. Now, this is a little bit harder than it was in the earlier case. So we let t of theta be the time it takes for the dart to hit the ground as a function of the firing angle theta. X of t of theta is, of course, d of theta. So our d of theta has this expression right here, v naught over b cosine theta times 1 minus e to the minus bt of theta. We can solve this for t of theta, which we do. Then we can put this back into our equation for y of t, setting y of t theta equal to 0. And now we've got an implicit equation for d of theta. And as with several other people have commented in this talk, this is often the first time students have seen an implicit equation for something like d of theta. This is the first time they've seen an implicit equation that actually really is physically meaningful. So that's an interesting result right then and there. Now, in order to maximize d of theta, we're going to need a numerical maximization tool, except that they don't make those. They only make numerical minimization tools. Well, having a minimization tool is just as good as having a maximization tool. Instead of maximizing d of theta, we're going to minimize the negative of d of theta. This time we find theta is equal to 40.68 degrees. Last time we found theta was 44.53 degrees without air resistance. So we find out that the angle that maximizes the distance has reduced a little bit further right there. And at this stage of our project, we have two theoretical models and, of course, our data. So the red model was our initial model without air resistance. The blue dotted and dashed line model is our model with linear air resistance. We see we've gotten quite a bit closer to the data here, but this linear air resistance model truly does not match the data right here. One more comment about dealing with students. It will often take me on the order of 5 to 6 weeks to get through this much of the project. I'm often teaching in a 10-week quarter. So I've often wrapped up using this project at this point, simply because if I want to focus on a different project or a different modeling topic, we are more than halfway through the term at this point. I believe Peter gets, again, at Texas A&M, he gets this project done quite a bit more quickly than I do. He also has a 15-week quarter as opposed to a 10-week. He has a 15-week semester as opposed to a 10-week quarter to play with. So that helps as well. So the next step is, neither of these models really truly matches the data. So can we, of course, do better? So we're once again returning to the modeling process. And the next thing we're going to do is we're going to try to use Buckingham's pi theorem of dimensional analysis to help us truly find the correct form of the air resistance term. So we're going to let F be the force due to air resistance, and we're going to start with the assumption that air resistance is going to depend on rho, which is our air density, the surface area of the object, which we're going to call S, and the velocity of the object, which is V. And then we're going to also include a dimensionless constant, which we call kappa in there. So our ansatz is that force is going to be our dimensionless kappa. It's going to be the surface area to some power A, which we're going to try to find. The air density to a power A, the surface area to a power B, and the velocity to a power C. We equate dimensions here. So m is mass, L is length, and t is time. So force is mass times acceleration. So that's our m. And then length per time squared is, of course, our acceleration. When we go look at our density, that's mass times length to the -3. So notice we have mass and then length to the -3, all raised to the a power. Surface area is length squared, so that's to the b power. And then our velocity is length per time, and both of those are raised to the c power. So we get the system, we get the following system of equations here. We get 1 is equal to negative 3a plus 2b plus c. 1 is equal to a, and negative 2 is equal to negative c. And that, of course, we solve that. A equals 1, b equals 1, c equals 2. So our force due to air resistance is going to be kappa rho surface area velocity squared. We let B, our air resistance parameter, involve the kappa, the rho, and the surface area. So the air density and the surface area are, of course, going to get tied up into our constant that represents, you know, the force due to air resistance. So at this point, we need to put our model together, and following the work that we've done in the prior models, especially with linear air resistance, if students try to put models together, often they will make those models look exactly like what we've got here. So when we started with no air resistance, the acceleration in the y direction was minus gravity, and now we need to have a term with air resistance proportional to the velocity squared. So I'll put in the derivative of y with respect to t and square it right there. Likewise with x, our only force is going to be due to air resistance. And I would invite you to just take half a minute right here and take a look at those equations. These equations are actually problematic, and there's some real big problems here. Can you notice what they are? So I would challenge you, can you see what problem there is with these equations? If you've got any ideas, please put those in the chat. Yes, those are nonlinear equations, and that is a big part of what the problem is here. Again, if you've got any ideas, please feel free to put those in the chat. And if you don't, that's also okay. You only got 45 seconds to think about this here, and that's not a lot of time. So there are a couple of problems here. These squared terms are always positive. So notice that the acceleration due to air resistance is always going to be in a negative direction. It's going to be negative here. And likewise with x. So since these squared terms are always positive, air resistance can actually act in the same direction as the velocity if the velocity is, again, in the negative direction. Another problem here, this is nonlinear. This really isn't a vector model. We just kind of took the y component and squared it and the x component and squared it, and we didn't think a lot about what we were doing there. We really need to realize this model as being a model that's about vectors and kind of start from this standpoint. This also is kind of a nice thing that I would really like to share with my students, because I don't think we see a lot of practical applications of our calculus 3, of our vector calculus material. So here we've got to let our position vector be a function of x of t and y of t. So position is a two-dimensional vector. Gravity works only in the y direction. And our model then, the second derivative of the position is, of course, our acceleration. Our gravity, so we have our gravity force, and then we're going to have the air resistance force. And now to get the velocity squared in there, we put in the magnitude of the velocity times the velocity vector. And we can then see that this vector formulation here is always going to work in the opposite direction of the velocity, which is exactly what we know. Which is exactly what we know it should. So yes, air resistance is nonlinear and should be a nonlinear term here. Let's hold that thought for a minute. Wait until I actually give you the proof of the pudding of seeing the final results here. So our initial conditions at time 0, x is at 0, y is at a height h. The derivative at 0, our x velocity, the velocity in x is v naught cosine theta. The y velocity is v naught sine theta. H is the height at which the dart is fired. Now, at this point, you might be able to solve these equations analytically, but I have never tried, and I would not even dream of having asking my students to try this. At this point, we're really going to be relying upon technology to do all of the analysis that we're going to do with this model. So first thing is, we teach students to translate second order and higher order differential equations into first order systems. And that's exactly what we need to do here because there aren't any differential equation solvers for higher order equations. We really need a first order system. So here I let R1 of t be my x of t, then R2 is the derivative of x with respect to time, R3 is going to be y, and then R4 is the derivative of y with respect to time. So the derivative of x with respect to t, or of R1 with respect to t, is R2, which is of course x prime. And then the second derivative of x with respect to t is just going to be the force due to air resistance. The derivative of y with respect to time, that's R4, that's just the derivative of y. And then the second derivative of y involves both our gravitational force and our term due to air resistance. We're going to do we can do parameter estimation in the same way that we've been doing. So if I just came at this by myself, I would have used an initial value problem differential equation solver, and then the numerical root finding algorithm to estimate my parameters. Peter thinks differently than I do, and at this point, he wanted to use a boundary value problem solver. I ended up programming both of those methods in order to put them into the modeling scenario, and results agreed to 3 significant figures. So we found the air resistance parameter is equal to 0.0645. Different than what we got with linear air resistance. Note the units are also quite a bit different because now we have air resistance is proportional to the velocity squared. The initial velocity has gone up to 12.3 meters per second. It was 10.26 meters per second with no air resistance and 11.23 with linear air resistance. So our velocity, our initial velocity, has gone up. We can use event location functionality with an initial value solver to plot trajectories. And you'll note that without air resistance, our dart travels the furthest. With linear air resistance, that pulls it in. And then with this velocity squared term air resistance, we pull the trajectory in quite a bit. And of course, we go a little bit higher because our initial velocity is, of course, higher. Now we're taking a look at all 3 models versus the data. So our data is in black, and this dotted green line right there, that's our velocity squared. So you asked, so air resistance is nonlinear. Yes, air resistance is nonlinear. This is one of these results that really makes me smile. And I think the next time I teach this project in class, even though I don't want to put students through all the work of programming this physical air resistance model, I would really like to go over this plot with them and talk about how to derive the model, because right here you really see the proof in the pudding at how closely that model follows the data, that now we really do have the correct air resistance term. And that's the sort of thing that absolutely makes me smile. Once we're going to try to find when d of theta is maximized, we use the fact that d of theta is maximized when negative d of theta is minimized. Using our scientific Python fmin routine, we can find that value. Using an initial guess of 45 degrees, we find theta is equal to 40.45 degrees maximizes the distance traveled. So that's just slightly less than what we found with linear air resistance. Next piece of the project, if anybody has time to do it, is to actually use a regression approach. So you can use the differential equation model with all of the data that's been collected to try to estimate your parameters. I use curve fit routine in SciPy in order to do this. In this case, with regression, our B, or our parameter for air resistance, was 0.0802. Without regression, we found 0.0645. We have our initial velocity again is a little bit higher, and the theta that maximizes the distance is 39.33. So that goes down a little bit. So we can compare all of our different results right here. And we can also, I'm just going to take a look at the 2 physical air resistance models. The one in pink uses all the data. It does a slightly better job at matching the data on the left-hand side of the graph. Those 2 models are very similar on the right-hand side of the graph. So we get just a slightly better result here. Again, once we've got the correct term for air resistance, we really are going to do an excellent job. We do just an amazing job of fitting that data. And that's what I've done, what we've done with this project. Thank you very much for listening today. If you would like to find the full modeling scenario, you'd want the teacher version up on Simeode. And I am also happy to correspond with anybody and talk about this. I really am glad that Peter shared this model with me and made it possible for me to share it with you. Are there any questions at this stage?
Can I please ask to say a little bit more about the experimental setup? So how you collect data?
Yes, so I am not sure exactly what Peter did, to be honest with you. He describes duct taping the dart to some apparatus that would hold it at a fixed angle and fire it. I know that he was firing it down his hallway and his wife was marking and measuring where it was that it landed. I bought some stuff at one of the local hardware stores thinking that I might try to recreate creating his data, but I've never kind of had enough time over the summer to do that. And I have not tried that in class because it just seemed like I could do some parts of it, like dropping a dart or firing a dart straight up. I think that with cell phone cameras, we could do a lot with, but getting a setup that really kind of fixes the Nerf gun at a known angle the physicists might be able to help me get some equipment better there. Did that do enough to answer your question, Victoria, or can I
Yes,
expand on that
thank
further?
you. Yeah, this was me. I will never build anything myself. I would rely on students collecting data or not physics department.
Mhm.
Yeah, exactly. But in your resources on SimioD, you have this data, right?
I do have the data. Yep.
Mhm. Thank you so much.
Yep.
Thank you, Jean Marie. That was really, really interesting and full of detail. Thank you.
You're welcome. Thank you for being here today, Beverly. Thank you for being here today, everybody. Well, I think we're just a few minutes off of the wrap up for the Simeode conference. So I think it's time for me to encourage you all to go over to listen to Brian's farewell address. And thank you all for being here today.
Hey, thank you for the talk. It was really cool seeing the model progressively get better, and it like told the story. It was like, hey, that's not that good. Oh, okay, it's better. And then at the end, that was a really, really nice plot. So,
Yeah, I love that. I love that graph at the end. Thank you for being here.
yeah. No, thanks. I was trying to get my video working, but thank you. Yeah.
Thank you.